Hi, I'm Elena and this is Thibaut, and we're both Integrated Biosciences PhD students in Dr. Petra Gruber's Biodesign Lab at the University of Akron. And today we're here at our university field station, which is in Bath Nature Preserve, a local nature preserve for the community, and it's only about 20 minutes away from campus for us.
Hey, so Thibaut here. I'm a French architect, and in addition to the PhD, I'm also a teaching assistant for natural science biology labs at the University of Akron. For the PhD, I'm studying biomimicry for architecture. And just in a few words, biomimicry is basically the transfer of biological organism strategies to technical systems. So we're looking at how different organisms are going to perform different functions and adapt to environments, so we can abstract those strategies and transfer them to our technical systems towards sustainability. And for the PhD, I'm studying mainly two different topics. The first one is growing fungal mycelium on agricultural waste in order to make sustainable building materials. And the second one that we're going to talk about today is looking at the morphology and growth of root systems in order to design better foundation systems.
Hey, it's Elena again. So I'm a local engineer from the Midwest. I grew up both in Michigan and Ohio. And also, while I'm doing my PhD, I'm a biomimicry fellow with three organizations: Biohabitats, Cleveland Water Alliance, and ODNR Office of Coastal Management. So I work part-time with them on design and engineering projects, bringing a biomimicry lens to that work. And I also get to do some field work also, which is pretty cool. So I study for my PhD biomimicry for coastal engineering, specifically for the Great Lakes, and I look at tree species that exist along rivers and coastlines, specifically their root systems and how they stabilize the shoreline and protect the shoreline.
One issue is that there is currently a lack of consistent biological root trait data in the literature, so it's difficult to compare results between studies and find trends. So we're working on a technique to get 3D models of root systems to have this kind of automated process to analyze biological root traits. And to get the 3D models, we're using photogrammetry, which is basically taking a lot of pictures from different angles of one object, in this case the roots, and then we upload those pictures to a software that will reconstruct the 3D model virtually, and then we can analyze this 3D model. And to use this technique, we really need to increase the accuracy to get consistent data from the root models, and also increase the accessibility so we can use it in the field.
So we want the most accurate 3D models of these root systems so we can get things like root branching angle, root length, and root diameter to inform the designs of our different engineering applications. So first in the field, what we'll do is we'll measure all around the root wad, root length, root diameter, so we can compare these in-field measurements to the measurements we get on the computer with the reconstructed 3D model. And you can see these different treatments here where we're trying to improve the reconstruction. So there are markers, colored markers on the roots. We've got powder, which is just flour from the grocery store to really enhance the object in the photos. Today is a really cloudy day, which is great, so we get very minimal shadows on the root system when we're taking the photos. So we'll take the same 3D model across different treatments and compare those in-field measurements to the computer measurements. And with this process, we're working with Claudia. She's an undergrad biology student, and she's helping us with this comparison process.
So we're also working on the accessibility part of this technique, because the goal is that anybody around the world with their own imaging devices could come to a root system, and they would take pictures following a specific procedure, and then they could upload those pictures to a database where we could reconstruct the 3D model. But it's pretty difficult to actually image complex systems in the wild. So it was really great to start at our local University of Akron field station, where we could actually experiment with the technique, for example, using a phone, a DSLR camera, or a drone, testing also different marking techniques, and use the space and tools that we have here at the field station.
So for this project, talking to experts has been really helpful, both in root biology and in photogrammetry, especially to help optimize this technique. And while the study is still ongoing, we've learned some key findings. One is that the number of pictures taken, as well as the addition of powder specifically and markers, seem to help with the accuracy of the reconstruction of the 3D model. And the type of camera used does seem to make a difference, but we've noticed phones that have really good quality cameras give us really good 3D models, which is helpful for the citizen science process.
So this has not been a linear but an iterative process. So for the last 2 years we've been optimizing these techniques, like getting slightly better each time. And we still are getting some mixed results between different experimental groups because our technique is slightly affected by the weather, for example shadows, or even like the wind moving some parts of the root system. And in some cases we also cannot access all around the root system to take the pictures that we want. But ultimately the results of this technique will actually lead to more sustainable bio-inspired design for building foundations and also coastal infrastructures. In the case of building foundations, the goal is to actually adapt the morphology of the foundation system to different environments. So for example, in cities we want less soil compaction to increase water infiltration and have less flooding. In environments like slopes, on slopes or coastlines, we actually want to prevent erosion. So the goal is to kind of integrate also multifunctionality, so we can also store resources and share them between buildings, but also with the environment.
And in the case of coastal infrastructure, for me, a lot of the practices used today are really old, traditional, and a lot of the infrastructure displaces natural habitat like oyster reefs and wetlands, which provide a lot of great ecosystem services. And something as simple as like a rock pile or concrete wall in front of someone's home can cause downstream erosion issues for the next door neighbor. That same concrete wall, if waves are crashing against it, can churn up the water, make it cloudy, so it's really hard for plants and fish to thrive. And so a lot of issues are caused by current infrastructure, which then is solved by even more engineering solutions, which completely changes our coastline. So what I'm hoping to do with the study of root systems is start to renaturalize our coastline by creating bio-inspired infrastructure that mimics nature in form, function, and material. And so what's really great about the field station, since it's open to the public, we can interact with people talking about our different research applications in the study of root systems. And in this video, we hope you've learned something from us today and about our research.
And let us know if you have any questions. Thank you.